Our understanding of acids and bases had been refined by Arrhenius's theory, and Arrhenius talked about acids as substances that furnish H plus ions in water, and bases as those that furnish OH minus in water. So, and you can see the problem. You can see the problem with a definition like this, that it only works for the solvent being water, and there are even though water forms as the solvent in majority of the reactions that we usually see in chemistry, there are still a large number of reactions that involve anhydrous or anhydrous conditions, that is, reactions that do not involve water. So there needed to be an extension of this concept of acids and bases, and that there came two scientists, Bronsted and Lowry, and together they did this work independently, and together they formed the Bronsted-Lowry definition of acids and bases. And it really depends on which geographic region you're from. Since Lowry was an English chemist in England, they still say it to be Lowry Bronsted instead of Bronsted-Lowry, but it still is the same theory. And it said something that's really simple, that acids donate H plus ions, and bases accept H plus ions. And as simple as that. The Bronsted-Lowry definition doesn't make use of any solvent, it doesn't make use of water, it just says that acids are the things that donate protons being the H plus ions, and bases accept those H plus ions. So that means you can still adapt the Bronsted-Lowry definition to the definition of Arrhenius. So the way you can do that, let's take NaOH for that example. And what NaOH does, NaOH is a base. NaOH is a base. We know that from Arrhenius's theory. And since it's a base, it has a tendency to accept H plus ions. And which species can it take H plus ions from? The only such species is water itself. So NaOH is technically just OH minus. OH minus takes an H plus and hydrogen ion from H2O. So this forms H2O, this OH minus taking an H plus ion from the H2O, and leaves you with an OH minus ion. So in this case, what we are seeing is not NaOH making the OH minus ion, but rather the H2O converting into the OH minus ion, because the OH minus takes the H plus ion. And that's something that you could have predicted by Arrhenius's theory, but we can extend our definition to even more general cases. So let's take two species, NH4 plus, that's called the ammonium ion, and add it to the sulfide ion, so ACE2 minus. And in a reaction like this is not a complete dissociation, by the way. In a reaction like this, you need to check either experimentally or by taking some numerical values, and we'll come to that in the later videos. But for now, take my word that this forms NH3 and HS minus. And what this means is that NH4 ion gives its H plus to S2 minus. So NH4, if you just do some logical operations in your mind, so NH4 plus minus H plus is equal to NH3, even though that's not a correct representation of the chemistry being involved, but you can still remember it like that. And AS2 minus gets added with that H plus that's removed from NH4, and that's equivalent to saying HS minus. And this is a way that you can remember this, but not the best way. You should represent this, let's say, in a scientific paper or a journal. So in this case, even though water is not represented in this entire reaction, NH4, since it it donates its H plus, NH4 acts as an acid. And S2 minus, the sulfide ion, since it accepts those H plus ion, it behaves like a base. It behaves like a base. And to study these acid-base combinations more effectively, there seems to be a tool set. There seems to be some definitions, and that's called the conjugate acid conjugate base system. So what that means, let's take the same example. Let's continue talking about that. So NH4 plus H2 minus, they give you, on the product side, you have NH3 and HS minus. And now what that means is that S2 minus gets converted to HS minus, and you're adding an H plus. You're adding an H plus, and NH4 plus gets converted to NH3. It gets converted to NH3 by removing the proton. And you could have done the reverse of this. If you instead took the product side and the reactant side, if you write this as NH3 plus HS minus, forming NH4 plus S2 minus, if you do that. And notice here, I'm not talking anything about the rate of this reaction, how forward this will go. I'm just simply saying that this is not a complete dissociation from both sides. Then in this case, NH3 behaves like a base. Why does it do that? So NH3 gets added with an H plus that it gets from the removal of an H plus from HS minus. And so this NH4 right here acts as an acid. S2 minus here acts like a base. This NH3 right here, we just saw it acts like a base since it gets added with an H plus. And this HS minus, since it donates an H plus, it acts like an acid. And this set of acids and base, this pair, is not really an accurate description. So instead of naming these as plain acids and base, we give them the name conjugate. So NH3 is the conjugate base of NH4 plus. And similarly, HS minus is the conjugate acid. Since HS minus here is an acid, but you can't really name it as an acid, it doesn't make sense to name it as an acid. You say it's the conjugate acid of the sulfide ion here. And notice once you do that, you can generalize this concept. So instead of having a specific definition, let's say you have a general acid, usually represented by HB or HA, just something with H. So let's write HA for acid, and it's added to a base. Let's represent it by B minus. And once you react it, you'd really let's just represent it with double arrows. Then that would form, since the HA would give away its H plus, so it would form A minus. It would form A minus by giving away its H plus, and that proton that it gave away, it will add it to the B minus. it to the B minus, and it will form HB. And so in this case, A minus is the conjugate base of HA, and HB is the conjugate acid of B minus. And the way you can remember this by looking at an example, what you can do is you can just see in which pair is hydrogen being removed. If the hydrogen is being removed, name the final product, in this case A minus, as the conjugate base. If you're adding hydrogen to something, that becomes the conjugate acid. And the great thing about Bronsted-Lowry definition is that you can extend it to not only aqueous solution, to not only things in liquid phase. You can also extend it not only in any solvent, but also in the gas phase. So if you had ammonia gas, NH3 gas, and you reacted it with HCl gas, you get a product. You get something that we know as ammonium chloride. And in this case, if you draw the Lewis dot structure of this, so NH3 and HCl, so HCl. Basically, this hydrogen here gets donated from HCl to NH3, and it forms NH4 plus and Cl minus, and these combine as an ionic compound to form ammonium chloride. And notice we don't need any solvent here. What we are just saying is that the proton is getting interchanged. But that sort of is the irony with Bronsted-Lowry as well. So consider a relatively strong acid. Let's say HF. It's an okay strong acid. If you put that in water, if you put HF in water, it is stronger. It is a stronger acid than water. So what it will do, it will donate its H plus to H2O, forming F minus. HF minus H plus forms F minus, and H2O plus H plus forms H3O plus, the hydronium ion that we talked about in the Arrhenius concept as well. So in this case, it acts like an acid. However, if you take the same acid in water as an acid in H2SO4, the sulfuric acid, now the sulfuric acid has a greater tendency to donate its hydrogen to HF. And it does so. What happens is H2SO4 loses its H minus, H plus, not H minus, to get to HSO4 minus, and HF gets added with H plus to give you H2F plus. And this really means that now, since you get a stronger acidic solvent, it converts the acid that you had in water to a base in this solution of sulfuric acid. And so that is the great thing about Bronsted-Lowry, and also its limitation, that it assumes everything to be relative to the medium, the solvent that you're taking the reaction with. So we have the Arrhenius theory and the Bronsted-Lowry for now, and we'll continue learning more about acids and bases in the next videos.